So now we will continue with chapter 5. So first, let's look at the problem of the standing wave. So when we have the light, so this is the resist. When we have the light shine on the resist, so some of the light will be reflected. So the reflection is given by this formula. So here is the resist. Here is the light coming in and reflected. The index here is N1, N2, N3. This is the substrate. So the reflection here is given by N3 minus N2 divided by N3 plus N2. So this is the reflection of the amplitude. For the power reflection is given by R squared. So this is like the reflection of the intensity. This one is like the reflection of the, you can consider this as the amplitude of the electromagnetic wave. So this is amplitude. So this is the intensity of the reflection. Something like this. So the light reflection. So now we have the reflected light and we have incident light. So they will interfere. So they will interfere constructively and destructively. So when they interfere constructively, you got the maximum, otherwise you get the minimum. So because exposure has different light intensity depending on whether it is constructive or destructive interference, then we have the after development, the resist it become a zigzag profile, something like this. To solve this problem, we can use the ARC. So this is called anti-reflection coating. It is a black color film that will absorb the light. So that means you coat a layer of ARC below the resist. Then the light will be absorbed by this ARC layer, so there will be no reflection. Another way is to do the post-exposure bake. So because of the resist, the thermal reflow, then it will be averaged out. So now let's look at more clearly. So here is the incident light. So this is the incident wave, and this one is the reflected wave, and this one is the standing wave. So this is the standing wave. This is a propagating wave. This one is the standing wave. So for the propagating wave, the lambda is given back here. So this is the lambda. So at this moment, this one is the maximum. At next moment, maybe here is the maximum. But for the standing wave, so at this moment, this one is the here. Half period later, it become here. So the oscillation amplitude here is like this. But at this point here, there will be no light intensity here. There is no light intensity. Now this one here is also maximum. So the pitch is from here to here. So this is the pitch of the standing wave. So you can see the pitch here is about half of the pitch here. That's what you see here. So the pitch is lambda over 2. In the resist, the lambda becomes lambda over the index of the resist. So the pitch is half of the lambda. So you see the same thing here. So this one high intensity correspond to this point. This is also high intensity correspond to this point. This one is low. Zero is maybe not zero. Low intensity correspond to this point. But actually, the standing wave come to here. So this is the standing wave coming to here. So this one actually will not be zero if the intensity this way and the intensity this way, E1, E2. If they are not the same, if they are not equal, E1 and E2, if they are not equal, you will not get zero intensity. So for the case of positive resist, so this part will be overexposed, more development overexposed. This part is underexposure, and this is the positive resist. So this is the standing wave. So now let's look at the photoresist. So photoresist consists of the 3 parts. So photoresist normally is a liquid mixture that can be spun onto the substrate to form a film. So it consists of 3 components. So one is the resin. So this is a binder that provides mechanical property. The second one is called the sensitizer, a photoactive compound. So this is the component that is sensitive to the light exposure. The third one is solvent. For example, n-butyl acetate, xylene, those solvents. So nowadays, people use more this solvent. The short name is called PGMEA. So this solvent is safer than xylene. So it is also possible to have the called dry. You can also buy the dry resist film. This is a kind of like a plastic sheet. You lay on the wafer. You roll it to make the good contact. So there is a dry resist film or dry resist sheet. But normally we do the semi coating for the application of the resist. So for the tone, so we have the positive tone and the negative tone. So here is the mask. So this area is exposed. For the positive resist, exposed area is gone. For the negative resist, exposed area remain. So for the negative resist, exposed area remain after development. So positive resist, exposed area is dissolved by the developer. So the most popular resist is the DNQ. So this one is developed in the 1970s, and it is still the most popular resist for today after 50 years. So this one is useful for the I line and the G line resist. So this is the wave loss for the mercury, argon. No, it's mercury arc lamp. Mercury arc, HG arc. It's for the mercury arc lamp. I line, G line for that, but cannot be used for the short wave loss. So the main component is the DNQ. So this is the DNQ. So this one is the photoactive compound. So the binder is a Novalac. So the binder here, the resin. So the resin is a Novalac. So this one is Novalac. So it consists of the aromatic ring plus 2 methyl group and hydroxyl group. So this one is like it will release hydrogen. So as a result, this one is soluble in a base developer. For example, KOH water developer. So this one will be soluble in a base like a KOH in the dissolved in water developer. So for the DNQ, this is the photoactive compound. So this one is this chemical structure. So this one is not soluble to this one. So this one is insoluble to this one. So it is called an inhibitor. As a result, so we mix the Novalac and the DNQ. We put them together. The overall it is not soluble. It is not soluble because this one protects this one from dissolution. So it reduces the dissolution rate of the resist in the developer because of this one. So this is how it works. So when we have the light, so here we have the N2 here. Should be something like N3 N2. So when we have the light, so this part will be broken. So here is the chemical reaction upon shining the UV light. So this part is broken, release nitrogen air, nitrogen gas. Then this carbon here come to this part, come to here. So it become something like this. So with the presence of the water, this one become something like this. So this is the COOH. This one is, we know it is acid. So obviously, so acid is soluble in the base developer. As a result, this one is insoluble before the exposure, and it becomes soluble after the exposure. So the net result is called differential dissolution rate is 100/1. That means before light, the dissolution rate is only 1%. The dissolution rate after exposure. We can also say that exposure by the UV light make it 100 times more soluble in the developer. So the developer is the base solution, as we said, KOH, NaOH. It can also be TMAH. So what is TMAH? It's trimethyl ammonium hydroxide. It is very similar to this one. So we know this is the ammonium hydroxide. So different is that this hydrogen here is replaced by the methyl group. So the hydrogen here is replaced by the methyl group. Then it becomes trimethyl ammonium hydroxide. So this is the most popular. This is much popular because here we have the metal. So we know that the potassium, the alkaline metals, they are not good for the transistors. So nowadays we use TMAH as the developer. But this one is used a little bit, not very often. This usually we make 2.6, we dissolve 2.6% of TMAH in the water to form the developer. So for the photoresist, we care about the resolution. This is the how small, how fine a feature can be resolved. Then is the contrast. This is the ability for the resist to distinguish between the exposed and unexposed region. This is contrast. So the resolution is mainly determined by the contrast. So obviously, higher contrast gives you higher resolution. And sensitivity is the light incident light energy needed to make the resist soluble in the developer for the case of the positive resist. So this is the energy needed. How many? The unit is the millijoule. So this is the sensitivity. How many energy per square meter, per square centimeter? So H resistance. So for the photoresist, it's photoresist. So resist means we use this one as the etching mask. So Novolac has this phenyl group, have this aromatic ring. So this one we know is chemically stable. As a result, the Novolac is pretty resistant to the chemical etching, resistant for the wet or dry plasma etching because this one is chemically stable. So we also want the resist to have the right spectrum response. For example, DNQ is good for the I line and the G line, but not good for the deep UV light. So now I give you some idea of how many photons we need to expose the resist. So here the resist is called a Kodak, but actually nowadays nobody uses Kodak. Now we use the resist from Shipley and AZ. Those are the Shipley and AZ are the most popular resist company nowadays. But now we take this Kodak as the example. So this one is the first is for the G line 436 nanometer. For this 436 nanometer, we can calculate the photon energy. So the photon energy is given by H Planck constant times the frequency. Frequency given by speed over lambda. So in the end, get this photon energy of this 433 nanometer photon. Then with this energy 150 millijoule, the number of the photons within this energy is given by 150 millijoule per square centimeter divided by this number, this joule. Then you get this number here per square centimeter. So we have this many photons per square centimeter. So the resist is about 1 micrometer. The thickness of the resist is 1 micrometer. So the area is a centimeter. Then we can know how many each photon, the volume by each photon. So the volume is given by 1 micrometer times 1 centimeter by centimeter, this number here, divided by the number of the photons, give you this photon. So each photon has this volume. If you do the 1/3 cubic, and this one, you get 0.67. This is the mean photon separation to expose this resist. You can see this number pretty much makes sense. So now let's look at the negative resist. The negative resist become insoluble in the regions exposed to the light. So it is a polymer with long chains. For example, this is the polymer. This one is the linear chain. So when we have the light radiation, we have the cross-linking. You can see this part is cross-linked. So when they become cross-linked, it becomes insoluble. So that's why it is a negative resist. So cross-linked area is insoluble, so it is the negative resist. So the developer is solvent, like the benzene, toluene, and xylene. And those are the developer for the resist. So because those solvents can remove the unexposed linear chain, but keep behind the cross-linked region. So this is the developer. So this is different from the DNQ resist. So for the DNQ resist, we use the QH. So those are the water-based developer for the DNQ, but this one is the solvent as the developer. So this is the negative resist. So in the negative resist is cheaper than the positive resist. That's why it is used before 1970s. But afterwards, people use more and more positive resist, because positive resist gives you better resolution. So one reason is that, so the negative resist gets swelled. So you can imagine, so those solvents, even though it cannot dissolve the cross-linked region, but those solvents, the molecule can get into the cross-linked region to swell it. When they are swelled, you lose some resolution. So this is one example of the negative resist. So we have the same thing: resin, photoactive compound, and solvent. So far we talk about the D and Q resist. So this is the traditional G line and I line positive resist. But this one has low quantum efficiency, called quantum efficiency. That means how many chemical reactions induced by each photon is about 30%. And also, it absorbs too much for the shorter wavelength. It would have very strong absorption if this is the resist. So the light comes in, then the top part will be exposed. The bottom part has no exposure because the light is absorbed by the top part. But this one is not good for the shorter wavelength. For the deep UV means 248 nanometer and 193 nanometer. So this one krypton fluoride, this one is argon fluoride, 193 nanometer. So this is deep UV. For the deep UV IC manufacturing, we use chemically amplified resist. So for the chemically amplified resist, so the effective quantum efficiency can be higher than 100. So that means, so one photon comes in, it can induce many chemical reactions. It can induce more than one chemical reactions. That's why we have the quantum efficiency much higher than 100%. But this is for the production, it's for the IC manufacturing. For research, we can have any, like even PMA is a good deep UV resist for the research. But normally for research, we only work with the G line and I line. So this is the idea of the chemically amplified resist. So what we have here is this thing is called PAG. So this is called photoacid generator. So this is the polymer chain, and this one is the insoluble. So this one is the soluble. So what we have? So we have the photoacid generator PAG. So when we shine the light, this one will generate the acid. And then we bake it. We do the bake, maybe 100 degrees for a few minutes. So during the baking process, so this acid will react with this insoluble set group, to make it soluble. At the same time, when during this chemical reaction, it releases a new acid. Then this new acid will make this one soluble, then release another acid. Then it will keep going forever. So basically, it is a catalytic chain reaction. So in principle, we need only one photon. To proceed one acid. Then we do the baking then we do the post-exposure bake. This is called the post-exposure bake to do the chemical reaction. So as a result, so the post-exposure bake is very critical for the chemically amplified resist. So this is the word. So post-exposure bake, so PEB. So now we look at the property of the resist. So first is the sensitivity and the contrast. So this one is called contrast curve. So what do we do? So we have the resist. So we shine the light. Then we do the development. So after development, here is the separate. After development, maybe it comes to here. This one, before development is here. So after development, it is here. So this is the remaining thickness, but this is the fraction of the remaining thickness. For this case, you may say correspond to here. So we have 75% of the resist remained after development. So for the case of the positive resist, so we know that for the high exposure dose, exposure dose, just the millijoule per square centimeter. For the high exposure dose, there will be nothing remain. So we have zero thickness. For the low exposure dose, all remain. So we have 100% thickness. So in between, we have this transition. So this transition defines the contrast. So it's defined here. 1 over log 10 df over d0. So df, the dose here is needed to clear the resist. So this is called sensitivity. So for the negative resist, we have the opposite. So high exposure dose all remain 100%. Low dose is all gone after development. So nothing left. So this is, we have the same sensitivity and the contrast. So what is the ideal case? So what is the ideal case? So ideally, what we want, So what we want is here. The ideal contrast curve is something like this, right? Come from here, they go down. So this is the ideal case. That means this is the ideal case. We have very, very abrupt, very steep transition. This way, if we see the df, this one equal to 1, so the bottom equal to 0, this one equal to infinity. So ideally, the contrast is infinity. As you see here, this is ideal resist. So gamma, the contrast equal to infinity. So d0 equal to df equal to critical dose. For this situation, so this one is the position here, and this is the dose. The different area have different dose. So this is exposed area, this is unexposed area. This one is the critical dose. So you can see, so this part here is all gone for the positive resist. So we talk about positive resist. So this area is all gone, and this area all remain. You can see here, this area all gone, this area all remain. Then it's all gone, remain, gone. So then no remain, gone. This way we get vertical resist profile, and this is ideal case. So in the real situation, so we have something df and d0, they are not equal to each other. So we have this. So this is the exposure dose. So this one is high dose, low dose. So for the case of the positive resist. So this one is high dose, so it is gone. Here the same thing. So here, at this point, here, at this point, we have the d0. So for the d0, so you can see, so d0 is the turning point to start develop and fully develop until df. So at this point, start develop and fully develop here. That's why you see the slope, the resist slope. You see the slope like this, because it corresponds to this part. So now we look at we will look back this one later on. So for the resist, we know the df and the d0. So for the light exposure, like we have this modulation transfer function MTF. For the resist, we define this CMTF. It's called a critical modulation transfer function. It is defined as df equal to 0 equal to this one, then it's given by this form. It relates depend on the contrast, depend on the lambda. So you can see for the MTF, we know it's better, higher is better. But for the CMTF, ideally, this is ideal case. If we have this case, then CMTF equal to 0. So that means CMTF lower is better. So the critical criteria is that CMTF equal to MTF. So this is the turning point. The CMTF equal to MTF. So normally we need the MTF to be higher than CMTF to have the resist height to maintain the resist height. So that means what we really want is the pattern height is the same as the resist thickness. So we want the pattern height after development the same as the resist thickness. Then we know the pattern is not lost. So otherwise, if the, for example, if the exposure dose is too high everywhere, so the pattern may become something like this. Right? The pattern may become something like this. Then we lost this part of the resist. Then we said it's not good. So when we have this critical threshold, then we know the pattern height equal to the resist thickness. So we can look at here. So here you can see, so this is the exposure dose. So dose is given by light intensity times exposure time. So this is the dose. X is the position on the resist. X is the position on the resist. So what we have, if the time is short, so too short exposure time, then the dose will be low. So we have the low dose. So we guess the dose is something like this. So when we have too long exposure time, the exposure dose become like this. So this one is the optimal exposure dose. But even for this optimal exposure dose, you can see the dose here is smaller than dF, and the dose here is bigger than D0. So that means the resist. So this is the thickness. If the thickness, so the resist will be something like this. So this is the resist. So the resist profile, if you look at it, so this is the resist. So the resist profile at this situation will be something like this. So the high load part, because less than dF, is not, this one is not developed to the bottom. So the low load part, this one is higher than D0. So you can see we lost some of the thickness, even though at this point. So this one, that means this is not enough. For this MTF is too low. The MTF is too low. So this one is okay MTF. For this case, you can see, so this part is higher than DF. So this part is lower than D0. So then the resist will be something like this. To the bottom, then to the top, then to the bottom. So the resist, the pattern height will be the same as the thickness of the resist. So this one is good. This is good. So at the critical information, at the critical point, CMTF equals MTF. So that means, so this one is equal to I max, I minimum, I max plus I minimum. So this is the critical. Yeah. So this is the definition of MTF, I max minus I minimum divided by I max plus I minimum. So we have this equation for this situation. If we do some arrangement, finally you will see that. So dF equals divided by I max equal to di minimum. So this is what you can define. This is what is the. If the exposure time is given by dF over I max and d0 over I minimum, this way you will get something like this. So this part will become here. It will be something from here, here to here and to here. It's called just enough. So just enough to have the resist pattern height the same as the resist thickness. For this MTF here, we can see it's a little bit over, a little bit under. That is more than enough. In this case, this MTF is a little bit more than enough. For this situation here, we say it's just enough to have the pattern height the same as the resist thickness. So what's the point of this? So previously we talked about a relay criteria. So for the relay criteria, so we have this light profile. So we have this. So you can consider this one is MTF. So this is the I max. So this one is I minimum. So this is the relay criteria. But for the relay criteria, it does not consider the property of the resist. So for some resist, this may be too good. For some other resist, maybe this is too bad. And that means this relay criteria is only a very rough criteria without considering the property of the photoresist. But by using MTF and CMTF, then we know for the particular resist what the MTF is needed to get the well-resolved pattern. The MTF may be higher than this relay criteria MTF, or maybe lower than this relay criteria MTF, depending on the property of the resist. So for the MTF, we have this graph here. So this is the MTF. So what do you do? So from this curve, you can find out MTF, and then you know the critical MTF of the resist. Then you know whether that particular condition, the resist and the lithography system, will be able to resolve a certain pattern or not. So this is the idea of the CMTF. So then this is a much better way to decide whether a pattern can be resolved or not than the relay criteria. So now we look at next topic is the grayscale lithography. So normal lithography is, we said, black and white. So we have the resist. So either a full height or no resist. This is the normal one. So grayscale means something like this. It is kind of a 3D pattern. So this is useful for the micro optics, like the macro lens. This is the macro lens array and other component for the optics. So one way to do the 3D lithography is to do the 3D photo mask. So if this is the chrome, and if this chrome you have different thickness, then it will transparent to different amount of the light. Then you have different thickness of the chrome. You have different light transmission through the chrome. Then you can create something like this. But this one is difficult to make. You need two lithography steps to make this 4 steps. So a better way to make the grayscale lithography mask is to use this one. It's called a pseudo grayscale mask. It is a binary black and white mask. It is still a binary black and white mask. So in this case, each of a pixel. This is like a pixel. It's filled with chrome, or a lot of chrome, or no chrome. For example, if this is the one of the pixels, this is 1 pixel. If we have one chrome here, then we say a 1% grayscale. If we have another spot here, then this is a 2% grayscale. If the pixel is fully covered, like this, we say 100% grayscale, something like this. You can see 0 to 1 is step of this one. So if this one is 0.1 micrometer, this spot is 0.1 micrometer, and the P is 1 micrometer, then there will be 100 grayscale steps. So this is how this thing works. So the requirement is that, so the feature size has to be smaller than the resolvable feature size of the lithography system. So that means that those small spots cannot be resolved. So that here you have one spot here, another spot here. But because the light don't have this very good resolution, so what you see here is like a blurred, like averaged. Is the average the pattern. You just say 2% transparent. You cannot tell there is one spot here or one spot here, because they are too close. They are too close to closure, too small for the lithography system to resolve. What we see is just averaged gray pattern. So this is the idea. But normally this process is very tricky, because the contrast curve this is not so reproducible. If we have the temperature increased by 2 degrees, then the curve maybe become something like this. So because of this, so this is very tricky, because the process is not so reproducible. So this example linearly snap the grayscale mask with 64 levels. So this one is 100% gray level. This is 0% gray level. You get something like this. You can also do something like this. So now we look at a step-by-step lithography process. So first one is the surface cleaning. So we bake it. We do the dehydration baking 100, maybe 120 degree to remove the water. Then we do the HMDS application. This is called adhesion promoter. Promote adhesion of the resist onto the substrate. This here said spin on the wafer, but actually the spin on is not good. But nowadays we do the vapor phase application of the HMDS. So now we will look at what is HMDS. So this is the website from MIT. So this is the ES. It's called Yield Engineering System. So this is the company that make the vapor phase HMDS. So what do? You use HMDS vapor to coat onto the silicon wafer. So this one is the HMDS. It's called hexamethyl disilagen. Something. This is HMDS. So on the wafer, so we have the hydroxy. We have hydroxy OH group on the wafer. Then we have the vapor of this one onto the wafer at more than 100 degrees. It forms this thing. It forms this thing. So this one NH become ammonia is gone. So we have the water. We have the water in the environment. So then the silicon methyl group. So the surface become the methyl group. So we know that the methyl group is hydrophobic. So methyl group is hydrophobic. So we have methyl group. So now we will look at the slide. So that means I will do it roughly something like this. So at the beginning, it is hydroxyl group. So after HMDS treatment, it become methyl group. So this one is the hydrophobic. So this one is the hydrophilic. So we have the developer, you have the resist here. And here is the substrate. We see silicon, the silicon here. So when it is hydrophilic, the developer is water-based, like this. This is the developer. When this one is, we have the hydrophilic, so the developer tends to come in between, Then the resist is peel off. There will be resist peel off. When they are like this, the same thing. Resist silicon wafer. If it is methyl group, then the water will not come in between the resist and silicon. This way, the resist will not peel off. So this is how. So this is how it help give better adhesion. So make the surface hydrophobic so that the developer will not get in between the resist and the silicon to peel the pattern off. So pre-bake to drive off the solvent, to drive away the solvent of the resist. Align and exposure, post-exposure bake. This one is needed for the chemically amplified resist. For the normal DNQ resist, we do not need a post-exposure bake. Develop, we can sometimes do the post-bake to make it more resistant to etching. So sometimes we do the post-exposure, post-bake to make it to harden the resist, to make it more resistant to the etching process. So now we look at the spin coating first. The spin coating. So the idea is simple. So we spin, we apply the resist, then we do the spin. We get in the end we get the very uniform film. So this is the physics, a little bit physics of the spinning process. So it depends on the property of the resist and the spin. So this is the property of the resist. So the most important part is the viscosity. So obviously, the higher the viscosity, the thicker the resist. So the other one is the drying characteristics. This is the solvent evaporation rate. For example, if the solvent evaporates so fast, if the solvent evaporates very fast, you get thick film. If the solvent never evaporates so slow, you get a zero thickness. You get very thin film. So normally we need some certain solvent volatile. For example, we can use the anisole, PGMEA, and chlorobenzene. So those solvents, they have the right evaporation rate needed for the spin coating. Some other solvent like acetone. So this is not good because this one evaporates too fast. You got not uniform film. For the spin, it mainly depends on spin speed. So this acceleration rate is not so important. The spin time normally we need to be higher than 40 seconds, then it is okay. So here is the SU8 resist. This is very popular resist for the MEMS, macro electromechanical system resist. You can see we have different SU8 with different amount of the solvent, with different amount of the solvent. For example, this one give you the thinnest resist. That means the solid percentage is the lowest. This one give you a very thick resist. So this is the solid percentage is very high. Can be like, for example, this one had 60% dry polymer dissolved in the solvent. This one is only maybe 5% of the solid polymer. So the higher the spin speed, the thinner the resist. So this is RPM, resolution per minute. So very often we do the lift-off process for the pattern transfer. As we learned before, so we have the resist the pattern, then we deposit the metal in the solvent. So the solvent will swell the photoresist a little bit, and then the photoresist will be dissolved. So the photoresist will be dissolved, then we leave behind the metal. So this is the lift-off process. So this is very popular for research and development. Very popular because it can pattern metals easily. So we know that metals like gold is hard to dry etch. So we cannot use plasma to etch the gold. So we can use the wet etch. We can use wet etching. We can do the wet etching of the gold. But for the wet etching, it's only good for the low resolution because the etching will etch laterally. So this reduces the resolution. For the high resolution, to pattern the high resolution gold patterning, so the lift-off is the best. But it is almost never used for the IC manufacturing because of the low yield. So we have the pattern etch is not very clean, and we have a lot of debris. You know the metal here become the debris. The metal here become the debris, and it can fall on other part of the wafer. For the lift-off process, this is the positive resist. Usually we get this profile, and this one is negative resist. We get this profile. So obviously this profile is good, so this profile is not good. For this profile, when you coat the metal, it becomes something like this. So the metal is easy to be gone in the solution. So for this profile here, we have the metal on the side wall. So the metal on the top and the metal on the bottom is connected by the metal on the side wall. Then the metal on the top is hard to be removed. So this is not good. Positive resist is not good. But normally, positive resist will work if the metal is thin. For example, if it is less than 100 nanometer with the metal, the positive resist probably will work. So why we have this profile for the negative resist? So this one because on the top we have the high dose. On the bottom we have the low dose. This is because of the absorption. Absorption of the light. The top part is overexposed. The bottom part is underexposed because of absorption of the light by the top part. As a result, there will be wider on the top and narrower on the bottom. So same is here. So overexposed wide, underexposed narrow. But this is the time. If you have the right exposure time, you get this. If the exposure time is too long, then it will become like this. Then it's not good. Not good. For this one, it may become like this. It will be better. So another way to have this undercut, we call this as the undercut profile, is to use two layers. So upper resist, lower resist. We have the lateral etching to give the undercut. So here we have the word IR. This is called image reversal. That means a positive radius converted to the negative tone by the flat exposure and the radius baking. If we want to know more about this image reversal IR radius, this is the one, AZ52014E IR. You can look at this website to see the property of this image reversal radius. This is actually a popular radius because this one works both as positive radius and negative radius. Okay, thank you.